Hi friends, this is your Prashant sir welcomes you to the world of physics from KH Patil P College, Hubballi. So in last class we have discussed about binding energy curve and characteristics of binding energy curve. So in today's class we'll just revise the things whatever we have discussed in last class, then we will move further. So first of all, what is meant by binding energy curve? So it is the curve obtained when a graph of a specific binding energy is plotted against the mass number of a nuclei. It is the graph of specific binding energy or binding energy per nucleon is plotted against the mass number of a nuclei. That means along y-axis we have taken a binding energy per nucleon or specific binding energy, and along x-axis we have taken a mass number and the graph is plotted. By plotting the graph we will get a curve, and that curve is nothing but binding energy curve. So this is about binding energy curve. And the curve is given, that means the plotted graph is given in your screen. Just have a look towards it. And in last class we have also discussed about the characteristics of binding energy curve. So the characteristics of binding energy curve are given below. Just have a look here. So the first characteristics of have a look towards the first characteristics of binding energy curve. Here it is. So first characteristic says that the binding energy per nucleon or the specific binding energy per nucleon is nothing but specific binding energy per nucleon for a light nuclei such as hydrogen 1 2, hydrogen 1 3, helium 2 3, helium 2 4, etc, etc are very low. So as lighter nuclei is concerned, so not only these elements, they are given some examples here. Not only these elements are known as lighter elements, but the elements with mass number less than 30, all elements with mass number less than 30 will be considered as lighter elements. So the mass number less than 30, the element with mass number less than 30 will be considered as a lighter element. And all the light elements have binding energy per nucleon very less. That means the binding energy per nucleon for a lighter nuclei, such a nuclei which has mass number less than 30 will be very low. And that means for such a nuclei the binding energy per nucleon will be very low. So this is the first characteristics of binding energy curve. So that will be represented here in a curve. That means in this region, the binding energy per in this region, from this graph it is clear that the binding energy per nucleon for these elements will be very less. So in that particular region the binding energy per nucleon is very less as compared to the other nucleons. So that will be explained from first characteristics. As the second characteristic is concerned, so in the low mass number region, have a go through the sentence. In the low mass number region, the curve shows maxima, that means maximum binding energy here, maximum specific binding energy for the elements with even number of protons and even number of neutrons. So the element with even number of protons and even number of neutrons will shows the maximum binding energy per nucleon or maximum specific binding energy. For example, carbon 612 and oxygen 816, helium 24, etc. These are nothing but the elements with even number of protons and even number of neutrons in the low mass number region. And minima is nothing but the minimum binding energy per nucleon for the element with odd number of protons and odd number of neutrons. So such as some examples are given here. Have a look here. Boron 510 and lithium 36. So these two elements have even number of odd number of protons and odd number of neutrons. And also hydrogen 1 2. It has one proton, one neutron. That means the number of protons and the number of neutrons are odd numbers. So such a neutrons have lower or minimum binding energy per nucleon. So that will be represented in the that will be expressed in your graph. We'll have a look here. Hydrogen 1 2, it is here. It is at the bottom of the curve. As curve is concerned, it is at the bottom. That means its binding energy per nucleon is very less because it has only one proton and one neutron, both are odd numbers. Therefore the binding energy per nucleon is very less. And coming to the point of helium is here. Helium is here. Suddenly for helium, the binding energy per nucleon increases because helium has two neutrons and two protons. That means both the number of protons and number of neutrons are even numbers. Therefore, the binding energy per nucleon suddenly increases. And for lithium, again the binding energy per nucleon decreases. Lithium is here. Again, the binding energy per nucleon decreases because lithium has 3 protons and 3 neutrons. Both are odd numbers. Therefore, the binding energy per nucleon decreases. And again, for carbon 612, carbon 612 has 6 protons and 6 neutrons. Both the proton number and neutron number are even numbers. Therefore, again, the binding energy per nucleon increases. And for nitrogen, again decreases. And for oxygen, again increases. So this clearly shows that the the element or the atom with even number of protons and even number of neutrons, that has a binding energy per nucleon. The binding energy per nucleon for those elements will be high. So the binding energy per nucleon is high for the element with mass with proton number and neutron number are even. And for their neighboring elements, that means the element with the odd number of protons and odd number of neutrons, for them the binding energy per nucleon is less. So this will be explained in the second characteristics. And further, therefore, have a look here. Therefore, it is clear that elements with even number of protons and even number of neutrons have a more specific binding energy, and hence they are more stable. So the elements with even number of protons and even number of neutrons have more specific binding energy. Therefore, they are more stable. And the element with even odd number of protons and odd number of neutrons, they have less specific binding energy. Therefore, they are less stable. So that will be explained in the second characteristics. So coming to the point of third characteristics, here it is. The curve shows that specific binding energy is maximum for iron. From the curve, it is clear that the specific binding energy is maximum for iron, and the atomic mass number of iron is 56, and the specific binding energy of iron is 8.75 mega electron volt. Therefore, it is clear that from the graph, iron is highly stable in nature because iron has the highest specific binding energy, per nucleon. So that will be clearly visible in the curve. Here it is. Iron is here. From if you look towards the curve, means iron has a highest specific binding energy. Therefore, it is highly stable amongst all the elements. So that will be explained in third property. And in as fourth property is concerned, the curve shows that for elements with mass number, the mass number which lies in between the 30 to 170. The elements with mass number in between 30 to 170, the specific binding energy is almost same as that of the iron. Andre iron the specific binding energy adalri ashta binding energy ಯಾವ ಎಲಿಮೆಂಟ್ಸ್ ಇರ್ತದ ಅಂತಂದ್ರೆ ಅದರ ಮಾಸ್ ನಂಬರು 30 ರಿಂದ 170 ನಡುವೆ ಇರಬೇಕು. ಸೊ ಅಂತ ಎಲಿಮೆಂಟ್ಸ್ ಎಲ್ಲಾ ತರದ್ದು ಸ್ಪೆಸಿಫಿಕ್ ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಏನಿರ್ತದೆ ಸೇಮ್ ಇರ್ತದೆ. ದಟ್ ಈಸ್ ಎಕ್ಸ್ಪ್ಲೇನ್ fourth property. Here it is. The curve shows that for element with mass number which lies between 30 to 170, the specific binding energy is almost same as that of iron, and that must be equal to 8.75 mega electron volt because the iron has specific binding energy 8.75 mega electron volt. That means in the curve from 30 means from here to I think from here to 170 means from here to here. So in this region, the specific energy is almost same. That must be equal to 8.75 mega electron volt. So that will be explained in the fourth characteristics. And fifth characteristic says that therefore it is clear. Here it is, fifth characteristics. Therefore, it is clear these elements are also highly stable like iron. So we know that iron is highly stable amongst all the elements. Therefore, these elements will also have the same binding energy of the iron. Therefore, these elements are also highly stable like iron because the elements with mass number in between 30 to 170, the specific binding energy is nearly equal to the specific binding energy of iron. That must be 8.75 mega electron volt. Therefore, these elements are also highly stable like iron. That will be explained by fifth property. And as the sixth property is concerned, here it is: binding energy is lower for both lighter nuclei and for both heavy nuclei. So lighter nuclei means the atomic mass number must be less than 30. For them also the binding energy is very less. And a heavy nuclei means the atomic mass number must be greater than 170. For them also the binding energy is very less. So in between this region the binding energy is more. So this will be cleared by observing the curve. So this will be given from sixth characteristics. And as seventh characteristic is concerned, here it is: the nature of the binding energy curve gives a clue to the release of energy in the nuclear process. That means nuclear reactions are present in the nature, and that will be clearly visible by observing this binding energy curve. So before binding energy curve, this binding energy curve gives an idea towards the nuclear process, that means nuclear reactions. That means in lower region, in lower mass region or lighter elements, they are unstable in nature. And heavy elements, they are also unstable in nature. Therefore, if any element that is unstable in nature, there will be reaction takes place, and that is nothing but nuclear reactions. So about nuclear reactions we will discuss later, not to worry about this. And in eighth characteristics, the curve shows that for element with mass number greater than 120, as the mass number is greater than 120, the specific binding energy decreases with increase in mass number. That means if you increase the mass number from 120, if you goes on increasing the atomic mass number from 120, the specific binding energy curve decreases. The curve goes on decreases. Specific binding energy decreases from mass number 120. That will be shown in the graph. That means from 120 means here approximately here it is. From here the specific binding energy goes on decreasing. So that will be clear from the graph, and that will be explained in eighth property. Here it is, eighth property. And uranium 235, have a look here. Uranium 235 is highly unstable in nature, and it is radioactive. So it is highly unstable in nature and it is radioactive. That radioactive branch we will study later. That about the radioactive we will study in the next later classes. Not to worry about that. But uranium, just remember one thing, that uranium 235 is highly unstable in nature, and hence that will gives one more process, and that is nothing but radioactivity. We will discuss in later classes, not to worry about this. So these are the some characteristics of a binding energy curve that we have already learned in the last class. So in today's class I am going to discuss one of the most important part about nuclear force. So have a look here. First of all, we will try to understand what is meant by nuclear force. So we know that the nucleus contains protons and neutrons. Those are nothing but nucleons. So these nucleons are tightly bound with each other or tightly held with each other with a strong attractive force, and that attractive force is nothing but nuclear force. Is this clear? That means nucleus contains protons and neutrons. So protons and neutrons together known as nucleons, and these nucleons are tightly bound or tightly held with each other inside the nucleus with a strong attractive force, and that attractive force is nothing but nuclear force. Is this clear? So that will be given here. Here it is, nuclear force. The nuclear force is the strong attractive force which hold all the nucleons together inside the nucleus is called nuclear force. Which hold all the nucleons together inside the nucleus is called nuclear force. This is clear. That means all the nucleons are held together, hold together inside the nucleus with a strong attractive force, and that attractive force is nuclear force. So is this clear? I think about the nuclear force is clear. That means this is a force, this is an attractive force, and it is an attractive force between the nucleons. It is the attractive force between the nucleons, and it exists inside the nucleus. So this much you have to remember. And this nuclear force has certain properties. So we'll try to understand the properties of nuclear forces one by one. So as first property is concerned, the nuclear forces are the strongest attractive forces in the nature. That means as attractive forces are concerned, there will be the gravitational force, there will be electrostatic force, and these are some of the attractive forces. And this nuclear force is also attractive force, and it is the strongest attractive forces amongst all these attractive forces. That means it is about 10 to the power 38 times stronger than the gravitational force. 10 to the power 38 times stronger than the gravitational force, and 100 times stronger, here it is 100 times stronger than the electrostatic force. That means the nuclear force is 10 to the power 38 times stronger than the gravitational force and 100 times stronger than the electrostatic force. Therefore nuclear forces are the strongest attractive forces in the nature. And as a second property is concerned, here it is. The nuclear forces are short range forces. Have a look here, it is very important. Nuclear forces are short range forces. That means we know that this nuclear force exists between two nucleons. That means one nucleon will attract the other nucleon with some attractive force. Is this clear? So that is nothing but nuclear force. But the one nuclei can attract the other nuclei only if the distance between these two nucleons will be of about 4 Fermi. Of about 4 Fermi. Here it is, about 4 Fermi. That means if the distance between two nucleons must be less than 4 Fermi, then only the one nucleon will attract the other nucleon. If the distance between two nucleons is more than 4 Fermi, then the nuclear forces will vanish and there is no attractive force between the two nucleons. This is nothing but the nuclear forces are short range forces. So have a look here, go through the lines. The nuclear forces exist between any two nucleons. The nuclear forces exist between any two nucleons separated by a small distance 4 Fermi. ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗಬೇಕಾದ್ರೆ ಆ ಎರಡು ನ್ಯೂಕ್ಲಿಯಾನ್ ನಡುವೆ ಕೇವಲ 4 ಫರ್ಮಿ ಡಿಸ್ಟೆನ್ಸ್ ಮಾತ್ರ ಇರಬೇಕು. 4 ಫರ್ಮಿಗಿಂತಲೂ ಜಾಸ್ತಿ ಡಿಸ್ಟೆನ್ಸ್ ಇದ್ರೆ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗೋದಿಲ್ಲ. ಸೊ ದಟ್ ವಿಲ್ ಬಿ ಗಿವನ್ ಇನ್ ದ ನೆಕ್ಸ್ಟ್ ಲೈನ್. ಇಟ್ ವ್ಯಾನಿಶಸ್ if the distance between two nucleon is more than that of a 4 Fermi. So therefore the nuclear forces are short range forces. That is, it is explaining the range between the distance between two nucleons. If the distance between two nucleons is about 4 Fermi, then there will be nuclear force, there will be existence of nuclear force. If the distance between two nucleon is more than 4 Fermi, then there is no nuclear force. That means one nucleon cannot attract the other nucleon. So therefore the nuclear forces are short range forces. That will be explained in the second property. And as third property is concerned, here it is. The nuclear forces are charge independent forces. Charge independent forces. As the nucleus is concerned, we know that there are protons, there are neutrons, and together known as nucleons. Protons are positively charged, neutrons are neutral in nature. That means charge of a neutron is 0. So now there will be attractive force between the proton and proton. There will be the attractive force between the proton and neutron. There will be the attractive force between the neutron and neutron, and there will be the attractive force between the neutron and proton. But independent of charge, that nuclear forces or the strength of a nuclear force, strength of attractive force is same, irrespective of charge. Irrespective of charge, the attractive force is same. The strength of an attractive force is same. That is nothing but the nuclear forces are charge independent forces. So have a look towards the lines here. The force of attraction between the proton and a proton is same as that of force of attraction between the proton and neutron, or neutron and neutron. That means irrespective of charge, the attractive force is same between all the elements. That means the force of attraction between proton and proton must be equal to the force of attraction between proton and neutron. Is this clear? And the force of attraction between neutron and neutron also same. Irrespective of charge, the force of attraction or the strength of force of attraction is same. So that is the thing, but nuclear forces are charge independent forces. So now the fourth property, the nuclear forces are spin dependent. That means the nuclear forces will depend on spin. As the spin of a particle is concerned, there will be two spins. One is up spin, and that will be represented by upper arrow mark. And one more is there will be down spin, and that will be represented by down arrow mark. Is this clear? uh, these nuclear forces are spin dependent means for parallel spins. That means for parallel spins means both the nucleon have the same spin, either up spin or either low down spin. ಒಂದು ಅಪ್ ಸ್ಪಿನ್ ಎರಡು ನ್ಯೂಕ್ಲಿಯಾನ್ಸು ಅಪ್ ಸ್ಪಿನ್ನರೇ ಇರಬೇಕ್ರಿ, ಇಲ್ಲ ಎರಡು ನ್ಯೂಕ್ಲಿಯಾನ್ಸು ಡೌನ್ ಸ್ಪಿನ್ನರೇ ಇರಬೇಕು. ಅಂಥ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ದು ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸ್ ಏನಿರ್ತದೆ ರೀ, ದ್ಯಾಟ್ ಈಸ್ ಸ್ಟ್ರಾಂಗರ್. Is this clear? So it is clearly given here the nuclear force between the two nucleons having parallel spins. Parallel spins means if both the nucleons have up spin or down spin is stronger than between the two nucleons having anti-parallel spins. Anti-parallel spin means one has up spin and another one has lower spin. ಸೊ ಪ್ಯಾರಲಲ್ ಸ್ಪಿನ್ ಇದ್ದಪ್ಪ ಅಂತಂದ್ರೆ ಅವ್ರದ್ದು ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸ್ ಏನಿರ್ತದೆ ರೀ ಸ್ಟ್ರಾಂಗರ್ ಇರ್ತದೆ. ಆಂಟಿ ಪ್ಯಾರಲಲ್ ಸ್ಪಿನ್ ಇರ್ತದೆ ಅಂದ್ರೆ ಅದ್ರದ್ದು ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸ್ ಏನಿರ್ತದೆ ಲೋವರ್ ಇರ್ತದೆ. ಸೊ ದಿಸ್ ಈಸ್ ಕ್ಲಿಯರ್ ದ್ಯಾಟ್ ದ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ ಆರ್ ಸ್ಪಿನ್ ಡಿಪೆಂಡೆಂಟ್ ಫೋರ್ಸಸ್. Is this clear? The nuclear forces are spin dependent forces. That means the nuclear force between the two nucleon having parallel spin is stronger than the nucleon than the nucleon having anti-parallel spin. ಪ್ಯಾರಲಲ್ ಸ್ಪಿನ್ ಇದ್ದು ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸು ಸ್ಟ್ರಾಂಗರ್ ಇರ್ತದೆ ರೀ. ಯಾವುದಕ್ಕೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಆಂಟಿ ಪ್ಯಾರಲಲ್ ಸ್ಪಿನ್ ಇದ್ದಿರ್ತಕ್ಕಂಥ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ನಡುವೆ ಇರ್ತಕ್ಕಂಥ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ಗಿಂತನೂ. So this clearly explains that nuclear forces are spin dependent forces. So that will be explained under fourth property. And as fifth property is concerned, the nuclear forces are non-central forces. Non-central forces. So as gravitational force is concerned, it is a force of attraction between two masses. That means that force of attraction is always along the line joining between the center of two masses. So this is known as the central force. As the electrostatic force is concerned, it will be that electrostatic force is an attractive force between the two unlike charges, and that attractive force is along the line joining between the center of two charges. But as nuclear force is concerned, this does not act along the line joining between the center of two nucleons. Is this clear? So therefore the nuclear forces are non-central forces. Therefore the nuclear forces are non-central forces. Look towards the lines here. The nuclear forces does not act along the line joining the center of two nucleons. Along the line joining the center of two nucleons. Therefore the nuclear forces are non-central forces. So this is the fifth property of nuclear force. And as sixth property is concerned, nuclear forces are saturated forces. Nuclear forces are saturated forces. That means as the nucleus is concerned, there are a large number of nucleons will be present. So one nucleon cannot attract all the nucleons present inside the nucleus. ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ದೊಳಗೆ ಇರ್ತಿರ್ತಕ್ಕಂಥ ಎಲ್ಲ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ನು ಅಟ್ರಾಕ್ಟ್ ಮಾಡಂಗಿಲ್ರಿ. But it only attract few nucleons which are just neighbor to the nucleon. ಈ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಜಸ್ಟ್ ನೇಬರ್ ಇರ್ತಿರ್ತಕ್ಕಂಥ ಆಜುಬಾಜು ಇರ್ತಿರ್ತಕ್ಕಂಥ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಮಾತ್ರ ಅಟ್ರಾಕ್ಟ್ ಮಾಡ್ತದೆ. ಬಟ್ ಹೊರತಾಗಿ ಎಲ್ಲ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ನು ಇದು ಅಟ್ರಾಕ್ಟ್ ಮಾಡೋದಿಲ್ಲ. ಸೊ ದ್ಯಾಟ್ ಈಸ್ ದ ಥಿಂಗ್. ಬಟ್ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ ಆರ್ ಸ್ಯಾಚುರೇಟೆಡ್ ಫೋರ್ಸಸ್. Go through the line here. That means each nucleon attracts only few neighboring nucleons, but not all the nucleons inside the nucleus. ಅಂದ್ರೆ ನ್ಯೂಕ್ಲಿಯಸ್ ತೊಳಗಿರ್ತಕ್ಕಂಥ ಎಲ್ಲಾ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ನು ಒಂದು ನ್ಯೂಕ್ಲಿಯಾನ್ ಅಟ್ರಾಕ್ಟ್ ಮಾಡಂಗಿಲ್ಲ. ಬಟ್ ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ ಅದರ ಆಜುಬಾಜು ಇರ್ತಕ್ಕಂಥ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಮಾತ್ರ ಅದು ಅಟ್ರಾಕ್ಟ್ ಮಾಡ್ತದೆ. That is nothing but nuclear forces are saturated forces. And the last property, that is seventh property, nuclear forces are exchange forces. That means this nuclear force exists because of there will be exchange of particles called pi mesons. That means if there is an attractive force between the two nucleons, means there will be exchange of particles called pi mesons. ಅಂದ್ರೆ ಎರಡು ನ್ಯೂಕ್ಲಿಯಾನ್ ನಡುವೆ ಎರಡು ನ್ಯೂಕ್ಲಿಯಾನ್ ನಡುವೆ ಒಂದು ವೇಳೆ ಅಲ್ಲಿ ಅಟ್ರಾಕ್ಟಿವ್ ಫೋರ್ಸ್ ಅದಪ್ಪ ಅಂತಂದ್ರೆ ಅಲ್ಲಿ ಪೈ ಮಿಸೋನ್ ಅನ್ನುವಂಥ ಪಾರ್ಟಿಕಲ್ ಏನಾಗ್ಲಿಕ್ಕತ್ತಾವ್ರಿ, ಎಕ್ಸ್ಚೇಂಜ್ ಆಗ್ಲಿಕ್ಕತ್ತಾವ. ಈ ಪೈ ಮಿಸೋನ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ ಇಟ್ ಈಸ್ ಒನ್ ಆಫ್ ದ ಫಂಡಮೆಂಟಲ್ ಪಾರ್ಟಿಕಲ್ ಆರ್ ಬೇಸಿಕ್ particle or elementary particle. About this you will learn in later classes, not to worry about this. But this is the element which is exchanged when there will be the nuclear force. This is clear. Have a look here. The nuclear forces are brought into existence due to the exchange of particles called pi mesons. Pi mesons exchange ಆಗೋದ್ರಿಂದನ ಅಲ್ಲೇನಾಗಿರ್ತದ್ರಿ ನ್ಯೂಕ್ಲಿಯರ್ ಫೋರ್ಸಸ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗಿರ್ತದೆ. These are some very important properties of nuclear forces. So please go through this and read one more time and have listen. Try to understand the concept very clearly. It is very important as examination is concerned. Have a look again and again. Try to learn the concept very clearly. Thank you very much.